Hi, I'm Yecheng Gong from Shanghai Foreign Language School, and today, allow me to present FireAce, an AI-driven intelligent drone swarm system for wildfire monitoring, a system that transforms how we fight one of nature's most devastating forces by making the invisible visible. Wildfires are wreaking havoc on communities worldwide. Each year, they claim over 30,000 lives and have destroyed nearly 47 million hectares of vegetation, an area roughly the size of Sweden. These fires release 1.7 billion tons of carbon dioxide annually and cause hundreds of billions in financial losses. According to the UN Environment Program, what makes wildfires so deadly isn't the visible flames we see on news broadcasts, but what remains unseen: ember tags. These burning particles travel kilometers through air currents, igniting new fires far beyond containment lines. UN research identifies these ember tags as the primary cause of wildfire destruction. Yet, our current monitoring systems, satellites, watchtowers, UAVs, and forest patrols share a fundamental limitation. They rely primarily on visual data. When smoke fills the air, these systems become virtually blind. More critically, they can't detect the invisible wind patterns that transport embers, leaving these deadly threats completely undetectable with current technology. This technological gap forces wildfire firefighters into a dangerous position, relying on experience and intuition rather than data and science when predicting fire spread. As climate change drives increasingly extreme fire behavior, this limitation becomes fatal for those on the front lines. Predicting wildfire behavior requires comprehending its underlying physical fields, or how temperature and wind velocity varies across space and time. These physical fields create the framework for modeling fire dynamics and enable firefighters to anticipate a fire's next move, transforming reactive response into proactive prevention. Current approaches fall into two categories: CFD and physics-informed neural networks that offer high precision but requires supercomputer resources and hours of processing, or computer vision approaches that provide fast detection but lose critical physics information and fail under occlusion. Neither approach meets the real-time requirements of emergency response, and Google's impressive 2022 simulation of the Tufts fire requires days of processing, far too slow when every minute counts in a real fire emergency. We can therefore identify 5 critical gaps that exist in current wildfire monitoring. First, physical field monitoring, capturing the invisible patterns driving ember attacks. Second, multimodality, capturing the interdependence between physical modalities. Third, real-time reconstruction, delivering actionable intelligence in time. Fourth, environmental resilience, ensuring robustness in harsh conditions. And fifth, prohibitive cost. Current systems at over $5,000 per unit make widespread deployment impossible in vulnerable regions. My research question becomes clear. Can an affordable drone swarm equipped with sensors and guided by physics-informed neural networks effectively detect and visualize the invisible physical dynamics that drive wildfire propagation in real time? Our goal is to tackle 2 challenges: the detection of invisible currents and the prediction of wildfire dynamics. We follow a 3-step framework. First, we deploy drone swarms to collect data. Then, we process the data to generate predictions using an advanced AI model. And finally, we provide firefighters with an interface visualizing these predictions, giving them the power to stop the fire before it turns into a catastrophe. FireAce goes through 4 development stages, each addressing a specific aspect of the wildfire monitoring challenge. First, I built a physical reconstruction engine that combines CNN feature extraction with physics-informed neural networks to transform sparse data into complete physical fields. Second, I designed path planning strategy that optimizes drone movement either through distributed coverage or gradient-based adaptive paths. Third, I designed a cost-effective drone swarm with integrated temperature and wind sensors, custom designed for under 500 gram per unit. And fourth, I carried out a comprehensive validation that ensures accuracy and reliability in real-world conditions. Together, these stages create a continuous perception action system that makes invisible wildfire dynamics visible for the first time. The core of FireAce is its physics-informed reconstruction engine, designed to capture both temperature and wind velocity fields. These fields are governed by 3 fundamental physical principles: conservation of mass, conservation of momentum, and conservation of energy. The math formulations you see represent these principles, which serve as constraints in our model training. To generate training data, I created a comprehensive simulation framework using CFD software with varying parameters of stove temperature and fan power. This systematic approach ensured robust model performance across diverse fire conditions. The neural network architecture follows a dual branch design, combining CNN and MLP components. We input the sparse data collected dynamically by drones into the CNN feature extraction block, which uses convolutional kernels to capture spatial derivatives and enables effective fusion of the multimodal data. The MLP branch deals with stacked static coordinates. By using separate embedding layers for data and queries, the operator network with the dual branch architecture allows high-dimensional generalization. We incorporated physics-informed loss functions during training, which ensure predictions respect fundamental conservation principles. In addition, we conduct loss function calculation with respect to many stages, including reconstruction and prediction, improving the model's ability to both transform sparse data into complete 3D fields and predicting 4D progression of wildfires. Validation shows our model achieves over 99% accuracy compared to just 75% for vision-based approaches, while maintaining computational efficiency with inference times under 1 second for a single slice of a field with an area of 100 square meters, fast enough for real-time disaster response. FireAids implements two path planning strategies, each optimized for different scenarios. Traditional zigzag path planning ensures static, complete converge, but requires approximately 800 iterations to converge. Our innovative adaptive path planning, guided by real-time gradient analysis. Drones collect data, and our neural network creates predictions. We then use that to guide the drones towards the most critical areas, typically where temperature changes rapidly and fire danger is the highest. This creates a powerful feedback loop. Better data leads to better predictions, which enables smarter data collection, reducing convergence steps by 75%, dramatically improving monitoring efficiency. Cost effectiveness was a core design principle, with each drone costing under 500 yuan, roughly 1/80th of the price of commercial alternatives. The drone integrates four key components: a basic quadcopter frame, temperature sensors for thermal detection, custom-designed 3D printed wind speed sensors, and a communication module. This lightweight, modular design ensures sensors can be modified or upgraded without redesigning the entire platform, while balancing weight constraints with measurement accuracy. Finally, we assemble the entire system together. The central control and terminal includes a main MATLAB interface, which is supported by Python modules for data processing and path generation, as well as Arduino C++ for drone command distribution and data collection in connection with the swarm. System-level optimizations were crucial for reliable swarm behavior. I implemented a state machine architecture with clear transitions between unlocked, takeoff, hovering, tracking, and landing states, ensuring predictable behavior and stable control. The communication protocol replaced reactive transmission with a state-based framework, where components transmit at fixed rates regardless of message timing. This was further enhanced through a multi-threading implementation that separated data transmission from command reception. And most critically, I designed a cascading frequency architecture that increases transmission rates at each level down the hierarchy. This includes algorithms to data hub, to the ESP32 modules, to flight control, ensuring smooth, reliable communication even in challenging environments. Experimental validation took place at the Intelligent Perception Laboratory of Shanghai Southern University, using a carefully constructed testing environment. Electric heating elements simulated heat sources, while industrial fans created controlled air currents. This setup allowed us to safely replicate the thermal patterns and airflow dynamics of actual wildfires. Vicon motion capture systems provided millimeter-precise drone positioning, enabling accurate correlation between sensor readings and spatial coordinates. The experimental process involved stabilizing the physical field, deploying the drone swarm, collecting temperature and wind data, and finally, progressively reconstructing the complete field. Quantitative analysis demonstrated FireAid's exceptional performance. The system achieved 94.1% accuracy in physical field reconstruction with adaptive path planning, outperforming fixed path approaches. And more impressively, adaptive path planning reduced convergence time from 2.51 minutes to just 1.57 minutes, increasing monitoring efficiency from 39.8 square meters per minute to over 63.7 square meters per minute. In all approaches, the system successfully converged to accurate field reconstructions, confirming its ability to effectively reconstruct physical fields in near real time, even with a limited number of drones. FireAids represents the first fully integrated system combining drone swarm technology with physics-informed neural networks, achieving affordable, accurate, and real-time reconstruction of wildfire dynamics. The system's innovative three-component architecture successfully integrates a multimodal physical reconstruction engine, a cost-effective drone swarm platform, and an adaptive path planning framework. Our experiments demonstrate high accuracy physical field reconstruction while maintaining real-time performance. Additional discoveries include the superior performance of adaptive path planning compared to conventional fixed path approaches, and the ability to achieve high fidelity reconstruction from sparse data by leveraging fundamental conservation principles. FireAids makes three significant contributions to wildfire science and management. First, enabling early detection of ember transport kilometers before visual confirmation, giving firefighters unprecedented insight into fire spread dynamics. Second, bridging the gap between theoretical fire science and field deployable technology, combining sophisticated physics-based modeling with computational efficiency. And finally, we democratized advanced monitoring technology by reducing costs to under 500 yuan per unit, making sophisticated physical field reconstruction accessible to resource-constrained regions facing the highest wildfire risks. The future impact extends far beyond technology. We envision protecting wildland firefighters, helping communities build long-term resilience, and transforming wildfire response from passive to proactive. Currently, FireAids is being deployed in pilot programs in collaboration with forest departments across China, and we'll expect to see the first-hand results in the coming month of wildfire season. Looking ahead, our work in the future will focus on two key areas. Firstly, hardware optimization to enhance the drone platform's resilience in hazardous fire environments through specialized thermal shielding, heat-resistant materials, and more powerful rotors capable of handling thermal updraft. Algorithm improvement, exploring more sophisticated model architectures, such as attention mechanisms, to further refine reconstruction accuracy for highly complex fire fields. Judges, with FireAids, we can finally see the invisible killer behind these disasters, transforming reactive firefighting into proactive prevention. Here, we make the invisible visible and the unpredictable predictable. Thank you.